Okay, so you guys were asked to tell some similarities between acids and bases. Let me take a see what we have. Okay, acids break stuff down and bases build stuff. Okay, that's not correct. I don't care who said it, it's fine. Remember, it's okay to be wrong. They form extra ions when dissolved in water. That is true. They do both have that in common. Yep, you listed the different types. So lemon juice is acidic. Water is actually neutral. It's neither. That's a trick question. Ammonia is acidic. No, ammonia is basic. Blood is slightly basic, 7.4. Milk is a little basic. Antacid is actually a buffer, but it's more basic usually, especially if it's Tums. Shampoo is basic. So a lot of those are wrong, but that's okay. There are compounds. Yes, they are actually. Acids and bases are all liquid substances. Kind of. That's half true, we'll say. Acids are liquid solutions are bases that are solute. Okay, kind of can read that. All right. So more examples of acids have a low pH actually, and bases have a high pH. We'll talk about that. Acids turn red on a pH. That's true. Bases turn kind of blue. They're both on the pH scale, which means for potential of hydrogen. And they increase a certain type of ion. That's true. Okay, so I've got a lot of good solid things there, and then I've got some that are misconceptions, which is kind of good to identify right now because I see a few things we need to talk about. But today we're going to be taking a look at what makes water a unique substance. Most of this we've talked about, cohesion, adhesion, polarity, hydrogen bonding. But then we're going to look at how the presence of other substances dissolved in water affect the properties of water. So if I gave you an ionic compound, is that going to dissolve in water? Everybody say yes. Yes, because ionic compounds have two ions which have a charge, and water is a polar molecule which has a positive and negative end. That's why water is so good at breaking down ionic compounds. So do you think acids and bases are types of ionic compounds? What do you guys think? Here, how about this? We'll poll you. How about I make, how about I make a statement? Yes or true or false? Ionic compounds, all acids and bases are ionic compounds. True or false? Acids and bases are ionic compounds. So if I add, I'm going to go ahead and just block that out now. So if I add an acid to water, it breaks down and becomes acidic. If I add a base to water, it breaks down and becomes a base or alkalinic. So now if I make the statement again and I ask you, or I say, acids and bases are ionic compounds, what would you tell me? Some people aren't going to change. That's fine. But if I told you it breaks down in water, and we know that salt breaks down in water, right, or dissociates in water, acids and bases do that. By breaking apart in water as an ionic compound, they become ions, and some types of ions create an acidic solution, like hydronium ions. Others create a basic solution, like hydroxide ions. So the statement is true. Okay? In fact, if I remove water from an acid, I have a salt when I'm left. What's the salt we've been playing around with? Sodium chloride, right? NaCl, table salt. Same idea. The only difference is table salt doesn't make an acid or a base. So water has many unique properties that make it an important substance for life. We just did a whole lab over them. And most of the unique properties of water result because water molecules form hydrogen bonds with each other. And when water freezes, that crystal structure forms due to hydrogen bonding, and it makes ice less dense than liquid water. You guys know this. This is kind of some knowledge you're supposed to come to me with. So what property of water makes Michigan so unique? Hopefully you guys maybe took a look at section 2. What property of water makes Michigan so unique? Let me list some properties of water for you. Cohesion and adhesion. There is its ability to insulate and retain a lot of heat. Because of that, it has what's called a high specific heat. So now, which of those 3 or 4 things I just mentioned makes Michigan so unique? Let's see what we're coming up with. Retains heat, high specific heat, insulation, yep. So I like that you've identified the high specific heat in the insulation. Here's why. And it's kind of a funny statement to make, but Michigan is so warm in the wintertime because we're surrounded by water. And I know that sounds really weird to say until you look at the states that are not surrounded by water at our same parallel. Let's look at Minnesota. Do they have happy-go-lucky winters? No. It's miserable there. It's like negative 30 sometimes, and they get way more snow than us, right? Okay? They should be identical to us. The only reason we are very warm in the wintertime, and yes, we are comparatively, like by 20 degrees, which is huge in the climate, right, is because we're insulated by water. So we do get a lot of nasty weather because of the lake effect. We know that. But all that water, that cold air, let's say, blowing across the lake does pick up a lot of moisture, but at the same time, it gets warmed. And it sounds weird, but our land is insulated too. Should we, by any means, be a state that grows cherries and apples? No. We're freezing cold. We got like ice cold winters. But our ground, the groundwater in our ground insulates our land so much, and we're surrounded by water, we don't have to worry about that. Okay, we can actually grow fruit here, which is really odd for how cold our winters should be. Okay? I know that sounds really odd, but if you think about it, it makes sense. I mean, we can grow grapes in Michigan. That doesn't make sense, does it? But we do. Let's see what else we have. It'd be even better if we weren't so close to the Arctic. That's true. That's true. Or closer to the equator. Okay. Yeah. Stop, Noah. Okay. I don't know. I was just going with the flow there. Like the water does, you know. No one got the water joke. Going with the flow? No? All right, so water can absorb a large amount of heat without changing temperature. This property can help organisms maintain a constant internal temperature. And Mr. Lorenz? All right. So water is able to retain its temperature in our bodies. That's very important. We love to maintain 98.6 degrees. If we fluctuate 4 degrees either way, we've got a serious problem, right? Brain cells start dying. That's not good. So the attraction of particles of the same substance, such as water, is called cohesion. We talked about this in a lab. Remember, cohesion is where you keep water from evaporating easily. Thus, water is a liquid at ordinary temperatures. And water molecules also stick to other polar molecules. We talked about that with the window. This attraction between particles of different substances is called adhesion. So if I asked you, which of these two, cohesion or adhesion, allows us to have bodies of water? Which of those two properties allows us to have large bodies of water? I only have 5 responses. Let's go. Co or ad? CO or AD? One or the other. What did you come up with? I'll wait till we get to 20. Come on. Couple more. One more. There we go. Cohesion, both. Oh, both, kind of both. Maybe not so much both. A little bit of both. Uh-oh. My board's freezing up on me. It's because we're talking about water. Cohesion for sure. Okay, so well, I want you to think about this for a moment. If water were to behave like nonpolar molecules, water is so little and small, and if it didn't have the ability to hold on to itself through hydrogen bonding, it would literally evaporate. I mean, it does evaporate, right? If it gets hot enough, you get enough energy, it will evaporate. Now imagine water is not polar anymore. It would literally be gone. It would just float away. So let me ask you, you did a lab yesterday. What was more cohesive? Was it alcohol or was it water? I gave you two polar substances. Who was more polar? Nobody put alcohol, right? So if our Great Lakes were a polar substance like alcohol, would they be here? No. There was not a strong hydrogen bond between those alcohol molecules in your isopropyl alcohol. So they literally could not hold each other on the penny, right? So a lot of you, your alcohol drops were half the number of your water, which makes sense because alcohol is way less polar. It doesn't have as much cohesion. It doesn't have as high of what's called an affinity to itself, an attraction. So water is attracted to itself, and because of that, water is more cohesive, and we're able to have bodies of water. So there are other polar substances. It's just they don't have that strong of a bond with each other, so they literally evaporate and dissipate. So this leads to solutions, putting things in water. So a solution is a mixture in which ions or molecules of one or more substance are evenly distributed into another substance. Salt water, right? That's a mixture, that's a solution. Now many substances are transported through living things as solutions of water, and dissolved substances can move more easily within and between cells. Now water molecules are going to dissolve many ionic and polar substances, but does not dissolve nonpolar substances. So we talked about this. Oil and water do not mix. Why? Oil is a covalently bonded substance. It is not polar. So some things you should remember from physical science that you want to write down so that you don't forget them. Water is what is known as a solvent. And if I add that to something called you guys remember what the other thing is? Solute, you get what is called a solution. Solvent would be water. Water is known as the universal solvent. Solute could be something like salt, right? Giving us salt water. So don't forget, the universal solvent is water. Here's the question, is alcohol also a solvent? It is. It's not the universal one, okay? Why? It's less cohesive and it evaporates. We're not made of alcohol. Okay? So this leads into things dissolving in water and becoming either acidic or basic. Now some water molecules break apart to form hydronium and hydroxide ions. If they do, they are said to be either an acid or a base. In pure water, hydronium and hydroxide ions are present in equal numbers. You need to know that a hydronium ion is an H3O+, and a hydroxide ion is OH negative. If I have extra hydronium ions, I'm an acid when I dissolve in water. When I have extra hydroxide ions dissolved in water, I am now a base. So acids and bases are compounds that change the balance of these ions. Let me give you an example of this. So this is what is called hydrochloric acid, HCl. If I were to dissociate these two in water, that would be my oxidation number, right? Everybody with me here? Okay. Remember, this is in the first family. It would like to give up one, although hydrogen really can't. We'll talk about that later. And then if I add that to water, we know that water has this kind of thing going on, right? It's going to yield something very special. I will separate my chlorine, and I will end up with a special ion called a hydronium ion. This is acidic because I have extra hydronium ions. pH is what we're talking about here. pH stands for the potential of hydrogen. I hope you guys are writing this down with me. I know it's messy. So then, let's say I have something else. Let's say I add this substance to water. Something happens. What ends up happening is I actually take this calcium bonds with oxygen, but who doesn't have somebody to bond with? So OH, right? And so what happens over here is I get in this, and I got to balance the equation. So I know Ca on the periodic table is what, +2? So I would really need to balance this and figure it out. But let's just, for simplicity here and not really teaching chemistry right now, let's just put those two together and, oh, I'm sorry, I put the wrong thing together. Let's just put those two together for right now. And let's just say we have these extra ones left over. And because of that, this is said to be what? Basic. So what is this right here? Calcium hydroxide. Dum-dum-dum. Yeah. So let's pretend I have an acidic stomach. Let me get a new page here. Let's just do this. Let's pretend I have an acidic stomach. Okay? And let's say I add something like calcium hydroxide to my acidic stomach. Who's going to bond to water? This guy? Here's what happens. So when you take calcium, here's what's going. I'm sorry. When you take a Tums, because you have an acidic stomach, you take this Tums, right? You're basically taking a base, okay? And this hydroxide is neutralizing H3O, because if I add those together, I get two H2Os. And I get a calcium supplement in the process, right? So what I'm really getting at here is this. H3O, a hydronium ion. That's a small O. Looks like a 0. There we go. What is this? That's a hydronium ion. And it's associated with an acid, right? If I add that to a hydroxide ion, which is a hydroxide ion, and that's associated to a base, and I add those together, I get what? What do I get? Two H2Os, which is neutral, right? The other thing I don't tell you, you always end up with a salt too, but you don't need to worry about that for this class. Okay. So what you're saying is water has the ability to be either an acid or a base, right? It just depends on what you put in it. And if you separate water one way, it becomes an acid. Separate it the other, it becomes a base. So we just talked about this, but if I have two water molecules added together, they have the ability to be split and become H3O ions or in a hydroxide ion. And you just have to understand that the potential to become acidic or basic is present in every water molecule. Okay? So acids are compounds that form extra hydronium ions when dissolved in water, and bases are compounds that form extra hydroxide ions when dissolved in water. And when acids and bases are mixed, the extra hydronium and extra hydroxide ions react to form water. So if I add an equal acid to an equal base, they will neutralize. So before I go over pHs and buffers, I want to show you a pH scale. So we're only going to mention this briefly. I'm hoping you've seen this before. So here's a pH scale. I don't know how many lines I have. 1, 2. Oh, good Lord. Who's this going to be? Ice, check for weapons. Check for weapons. It's not Al-Shabaab. It's not the Taliban. It's Miss Atkins. All right. All right. Everybody say hello, Mrs. Atkins. So you're on YouTube now. Yay. She's giving out money. Hey, give me $1. Oh, yes. What kind of question is that? Yeah, right here. Oh, there's boxes here in my closet. Just go right there. What? In the closet. In the closet. Yep. Okay. Yep. In the closet. Okay. All right, you guys. So if I were to ask you from last year, just polling your present knowledge, how many numbers are on the pH scale? I'll let you answer that while I draw my dealio up here, because I don't like the drawing I was getting by doing it on this device. Let's see what you guys came up with. 14, 0 to 14. 18. 1,000. 14. Ooh. 7. Okay. Mixed review. That's okay. So let's go ahead and make the pH scale together. And you could potentially get down to 0, but it's impossible really, so we won't worry about that. Well, in a lab, you could make 0 in a lab. The pH scale that we reference in biology is what you find in living natural systems. This pH scale is not even close to what you can get as far as like molarity is concerned in labs. But again, that's chemistry stuff that you worry about next year that doesn't matter in real world. Okay, so we're going to talk about real world things in here, not the stuff that only matters in the lab. So if I look at a pH 1 through 14, let's say, 1 being extremely what? Acidic. So as I go from 7 being what? Neutral, to 14 being what? Basic. As I go this way, my hydroxide ions are going to increase, right? And as I go this way, my hydronium ions are going to increase. And in the middle, they're equal. That means I have H2O here in the middle, right? So understanding the pH scale is great, but now I got to give you one more piece of knowledge. The pH scale is exponential, which means it's in a matrix, which means it's going to exponentially increase by a given number, and that number happens to be 10. So if I go from 7 to 8, that is 10 times more basic than 7. So every jump is going to be, every time I go, it's times 10. So how about if I asked you, how many times more basic is 10 than 7? You go 10 times 10 times 10, which is 1,000. So 10 is 1,000 times more basic than 7. You guys understand that? That's pretty important. So our stomach acid is like down here in the 3 range. Okay? It's actually a little bit below that. Sometimes 1. So our body, do you know what our blood is? Anybody know what our blood is? It's 7.4. Okay? So is breast milk. That's why babies need to, that's what milk is. Slightly basic. Okay? And so understanding where things fall on this scale lets you kind of get an idea of how more acidic or basic something is. Now, if our stomach is down here, anybody know what your pH, the pH of a pop is, like Coke? It's right down there with stomach acid, okay? So I'll tell you this, every pop you drink will shift your pH 1 point. Roughly. Up to a certain point. Then it's not going to turn your blood into acid, but one pop will shift your pH 1 on the pH scale. So, yeah, your regular can of Coke. So if this happens after 1 can of Coke, folks, and you've turned now your blood into an acidic solution rather than a basic solution, what do acids do to things a lot of times? They eat them and break them down, right? So do bases, but your body likes 7.4 or basic, and so it's built to handle that. It's not built to handle acids. So when you drink a pop, you're literally eating all of your blood vessel walls or breaking them down. Not eating them, but you're corroding them, we'll say. Okay? So one more reason to not drink pop, right? Oh, here's another one. Where do you make all your blood at? Kind of. Bone marrow, ding, 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 ding. And your bones is where you make all your blood. That sounds like an awesome idea. Let's put an acidic solution through our bones. If you drink 1 pop a day and you're a woman, you're 80% more likely to develop osteoporosis, which is basically spongy bones. So if you wonder why people tell you pop's not good for you, that's why. I don't even allow it in my house. Yes. Well, if it's acidic, it could be just as disruptive, but it's really the sugar that's the issue. Okay? Sugary beverages in general. Okay? So here's the question. Can a basic solution just be just as caustic as an acidic solution? Yes. Stick your hand, don't do this, but stick your hand in like bleach overnight. It's not going to be there in the morning. Okay? It will eat it up just like an acid would. Same idea. Okay? Don't test that theory. It will hurt. Okay? You'll be crying. So the pH of solutions in living things must be stable. Hey guys, I'll give you an opportunity for input in a minute. We like a pH of 7.4, except for our stomach. Our stomach likes a pH of like around less than 3, hydrochloric acid in there. That breaks everything down. Why doesn't our stomach eat itself? Oh, did I skip one? No, I did do it, but I'll leave it up there. Each pH is measured of how acidic or basic a solution is. Each 1 point increase on the pH scale represents a 10-fold decrease in hydronium ion concentration. That's what we drew out. And the pure water has a pH of 7. Acidic solutions have a pH below 7 and pH basic above 7. Okay. So we need to have a way of maintaining 7.4. Folks, our blood, I should say, is a combination of both acids and bases floating around in that bloodstream. Overall, we are slightly basic. Why is it good to have both in our blood? How about this? What if I drank that pop? Let's say I drank a 2-liter. I've seen kids do it. Okay? So, you guys, don't just blurt things out. Shh. Let's say I drank a 2-liter of pop. That would literally change my pH from 7.4 if I weren't a buffer solution to probably right around 4. And then I'd really feel it. Okay? So, gentlemen, we have both acids and bases. And when I add a base to an acid, it neutralizes it if it's equal amounts. That's known as a buffer. So our blood has buffers built into it so that when we drink something like a pop, it doesn't destroy us completely. Now, pop is nothing that you would ever pick off a tree, right? It's like concentrated sugar beet, okay? Now, if you ate the sugar beet, you'd be able to deal with that slight pH shift with all the buffers in your bloodstream, and your pH would not shift at all. But when you drink a pop, which is basically concentrated sugar beet juice, okay, well, distilled sugar beet sugar, so much there's no water left, okay, and then you put that into your body, you're creating an unnatural environment, right? Like nobody 100 years ago was drinking pop. They were, however, picking fruit off a tree and eating it. So that's the kind of way you should think about it. Like I can eat an acidic orange or an acidic apple because they're very acidic fruits. But they don't do what a pop will do to me because it's not concentrated, right? And my body can handle that. It can buffer that out. But I cannot buffer out a pop, okay, as well. So buffer is basically a substance that reacts to prevent a shift in the pH. And if you're eating a normal human diet, which is not KFC, which is not McDonald's, which is not Coca-Cola, which is not Pepsi, there's none of that. I'm here to tell you, if it wasn't a food 100 years ago, it still should not be a food, okay? But taking all of those unnatural things out, if you were to eat a natural diet, your body's pH would not fluctuate. It wouldn't. Quick summary, and I'll give you your homework. The hydrogen bonding between water molecules explains many of the unique properties that make water an important substance for life. We talked about cohesion, adhesion, how water has a high specific heat and is able to retain its temperature. And then acids and bases change the concentration of hydronium ions, H3O+, to make things more acidic. And the pH of solutions that have an increase of hydroxide ions or bases goes the other way on the pH scale. And the pH of solutions in living things like us must be stable. For us, that happens to be 7.4.